Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future. So after the lecture, yesterday Tobias told me that when I say I'm going to now switch to the physical architecture, there was reaction like, not again. And so I promise I'm going to keep it short and sweet, because in fact, we've already seen a lot of physical architectures in the lecture. So it's there's nothing really very new, and the little bit that's new, we are not going to get too deep into it. So first, no surprise, we replicate a little bit. It's a little bit like in MongoDB that we have multiple servers that replicate the functionality of the graph. That was in the early versions of Neo4j that there was no sharding. They just had multiple machines and all the machines worked on all the data. And so what you can achieve with that is that when multiple people read the same data, they can just be spread all over the machine. So you can do some load balancing, just like for a website. For writing, you have a mode where people are only allowed to update this database right here, and then it propagates to the other ones. But then at some point, they also made it possible to write all over the place. But then you have the CAP theorem that kicks in and all the difficulties that have to do with that, right? So similar to MongoDB, we replicate for the same data on multiple machines. Now, what about the sharding, right? There's replication and then there is partitioning. So the sharding, that is actually a difficult problem. When I started teaching big data, it wasn't solved yet. So I just had to say, you know, sharding is not solved and we cannot shard graph databases. But this actually changed. A lot of things have happened in the past few years. And the first people that I'm aware of that actually solved it is the Oracle team with PGXD. PGX is the name of their graph database, just like Neo4j. And PGXD, D is for distributed. And they actually managed to spread it and shard it over multiple machines. They even gave a guest lecture on PGXD several times. So the trick here is that you partition the data similar to how we did it for tables or trees. You spread it all over the cluster. But the difficulty for graph databases is that you need to be able to efficiently traverse through paths in the graph. So the way you do it is that when you shard the machines, you don't shard it in a way that doesn't overlap, right? For trees, you just don't overlap. You strictly separate. You have your partitions, you spread them. For graph databases, when you shard, you arrange that there is a bit of overlap. It means that parts of the graph are actually across multiple machines. And then what happens is that you traverse the graph, then you arrive to a part that is in an overlap. And for that overlap, you then jump to the other machine and then continue over there, right? A little bit like in some, I think Apple, when you move your mouse to the corner of the screen and then it just moves to another computer, right? So similar to that. So it's not easy at all. There's a lot of performance aspects based on the patterns of the queries and so on. So very, very complex, but it is solved. And now Neo4j also started sharding, and most of the graph databases, database providers are actually providing a way to shard the data. Okay, so that's what I'm about to say about sharding. It is now considered to have been addressed. Now, what about the physical storage? You know, like for document stores, for example, it's done with Bison that we store the data. Well, here you need to look at the memory and at the disk. In the memory, I told you about this index-free adjacency. That means that you have pointers in memory. So it means that the labeled property graph that is in the memory is actually just actual memory pointers, all the edges. And you basically have to visualize something similar to you know, Java classes, where you have objects that point to each other and that have a complex structure in the memory. But this is all efficiently stored in memory. And the graph that you see here is very close to the actual graph of pointers that you get in the memory of the computer. For whom is that clear? Okay, very good. All right. And then you have all kinds of tricks in order to efficiently move over between all the places that you can go for a single node. You can consider all the edges. If you have an edge, you can consider all the nodes on both sides of the edge and so on. So there's nothing really, you know, if you know object-oriented programming, then that gives you a good visual of that. Now, when you store it on the disk, for the long-term durability of the data, you store everything separately. You have the nodes, you have the edges, you have the properties, you have the labels, and so on. And so do I have it here? Yes, exactly. So you have what's called the node store. It's a bunch of files that just store the nodes, and then a bunch of files that store the edges, the relationships, and then a bunch of files that store the properties that the nodes and edges have, except the strings and the arrays. So these things, so these are the homogeneous lists of atomic items, atomic values, and these are the strings. These are handled separately because they can actually be very dynamic in size. But all the other atomic values, the properties, atomic values, they are in the same file. And then you have a label store, right? So this is really very nicely. It's so Swiss to do it like this. Who knows Ursus Verli, like tidying up art? Maybe no longer, okay. So it basically means you tidy everything up, put the nodes with the nodes, the relationships with the relationships, the properties with the properties, the labels with the labels, right? And so when you load it from this, then you reconstruct this graph in the memory, and then again, you persist it back to disk when you put it there, okay? Now, to give you an example of what there is in memory, for example, when you have multiple labels associated with a node, it's just a linked list, right? That you go through whenever you query dynamically. And then when you have edges, you basically have this doubly linked list in all of the edges that go out of a node and come to a node. The direction doesn't matter. And then you have this doubly linked list that allow you to iterate over all the possible ways you can exit and enter a node. To whom does that make sense? Right? Very good. And so this is used as a primitive for executing Cypher on top of that. Whenever you look for a pattern, you use all of these structures here in memory to find the pattern. And what I shortly mentioned yesterday is that on top of that, you can also have index structures that accelerate finding, for example, the nodes that have a specific property that you can have with hash indices or tree indices, right? To not have to search for the entire graph and directly spot the nodes that have specific properties. Okay? And that's all I'm going to say about the physical level. And what I want to conclude with on Neo4j is with absolutely excellent news, and that is between last year and this year. This is actually new. It didn't exist last year, at least not in that final form. I told you that for trees, there's many languages, and we still haven't consolidated. For tables, it is consolidated. That's SPARQL. And for graphs, people at last reach an agreement. So there are two standards, but they are both meaningful. So first, there is the GQL standard that is, in fact, Cypher standardized, if you want to put it that way, right? So it's basically an agreement between many industry players to harmonize their query languages, and a lot of what is in GQL actually comes from Cypher that I taught you. So essentially, you basically learned GQL. You can actually go to that blog post right here. It's a very good, gives you a good feeling of how things actually work, because Neo4j basically announced that it's been standardized. And what they told their users is that they are going to smoothly evolve Cypher to basically align it with the standard, so that at the end, they will essentially support the GQL standard. But they will do it smoothly because, of course, their users already have a code base in Cypher. So this is going to be done over time. All right, so this is GQL. That is essentially the standardized Cypher. Not to be confused with GraphQL. GraphQL has nothing to do with graphs. I have no idea why they call it that way. GraphQL is about trees. This is the 26th query language for trees. But this is really something different here. GQL is really specifically for graph databases. Then we have SQL/PGQ. This is basically an extension of SQL. So it's just the SQL language that selects from where and so on, the language you all know. Extended with pattern matching. Pattern matching is the ASCII art, right? This is really the core of what makes a graph database, like the top use case. And so SQL PGQ is basically just that. You extend SQL with graph pattern matching. So it is good for the people who are still in the environment of a relational database, but they also want to deal with graphs. And so what I would expect to happen is that products like PostgreSQL or MySQL or the really typical relational database management systems, that they start supporting graph types. They add to their system some way to support graphs. In fact, in a similar way than PostgreSQL supports objects and arrays, right? Now, in the latest versions, actually do have some SQL extensions that deal with JSON types, right? So these are the two big standards, and that is something that I am really delighted about, because this is exactly what we wish for, that we have one standard and then all the industry players focus and align to the standard. Okay. Any questions so far about Neo4j? Who is with me? Okay. All right. So then I'll move on to something different, which is the before I do that, just to mention, there is also a Spark implementation of a graph database. It's called GraphX, and that's on top of Spark, right? So just so you know, and if you want to take a look, you can, because you're already familiar with Spark. You're already familiar with graph databases. All right. So that was about labeled property graphs. Now I'm going to turn over to the second paradigm of graph databases, which is triple stores, and RDF is the known standard for that. Who has ever heard of RDF? Okay, so some of you, but not everybody. All right, so it's a W3C standard, so it's a standard just like HTML, HTTP, XML, XQuery, and so on, so in the W3C. And the best way that I think I can introduce it is the question that one of you asked over Zoom yesterday. Why do we have labels on nodes, and why don't we use properties? Like, the label property graph is basically too complex, and we can simplify it further without any loss of generality. In fact, that's exactly what triple stores do. The idea is that when you have in a label property graph a node with, like, let's say 10 properties, in a triple store, you will shred it further, taking each property apart and make it 10 edges and 10 nodes. So instead of all the properties in a single node, you just decompose it further into an even more fine-grained graph. So it means that in a triple store, you just have nodes and edges and labels on the edges, and this is it. This is it. And it's really just more fine-grained than a label property graph. So now, it means we just need these three ingredients: nodes, edges, and labels, and the labels are only on the edges. And so the reason that this paradigm is called a triple store is that everything in there, just like in JSONic, everything is a sequence of items. Here, everything is a triple with a subject, a property, and an object. You can think of them as basic English sentences with a subject, a verb, and an object. Like ETH Zurich is located in Switzerland. This is a triple. And this is basically to say that when you have a triple store, it is just an absolutely enormous list of, let's say, 1 billion triples like that. And when you take the 1 billion triples, together they form a graph, because the subject and the object, of course, will also have further edges going to them and coming from them, right? So in fact, this is all organized in a very big graph, the one that looks like this, right? So you see here, I have 5 triples in this graph over here. Okay, so this is why it's called the triple store. Now, what about the names of the nodes and the labels? So let me tell you, there's 3 possibilities, in fact. The first possibility is to use URIs. Remember URIs? This is what identifies a resource. We saw it previously for namespaces, also for REST APIs, and so on. And so basically, it's W3C, and they are the ones who basically standardize the web. So when they needed to find a way to give a name to the nodes and to the edges in the in RDF, they basically thought, let's just eat our own dog food and let's just use URIs, right? As a parenthesis, normally today we are supposed to say IRI. That's the official name. I never hear anybody say IRI ever. So it seems that nobody actually started using that terminology. Most people still say URI, right? So I tend to also say URI because of that, but don't be surprised, but you can consider that it's the same thing. It's just these long strings that start with a scheme, very often HTTP. All right, so we identify many of the nodes with a URI like this. The same goes for the properties, so for the edges. We label them also with the URIs. For example, this URI is the URI of is located in, right? Then what I can have for the nodes is also, instead of a URI, a literal. That could be a number, that could be a string, that could be a date. For example, you could say Switzerland has a population of 8 million. And then the object node doesn't have a URI, it just has a number, 8 million, right? So this is then called a literal. And here you have, because again, that's W3C, they standardize XML and so on. So all of these literals follow the XML schema standard. It's the same as in JSONic, the same atomic type. So that's also you already know, right? I don't need to cover it again. And the third way that you can build the nodes is to just leave it blank. You basically have a node, but you don't give it any name or you don't give it any literal. For example, that would be the ground on which ETH is built, right? You don't need to give it any name. You just say ETH is built on ground of something. It's just a placeholder for the ground, and that ground is a subset of Switzerland. That we call a blank node, right? That can also be used as a placeholder for data you don't have yet, right? You just know it exists, you just put a blank node in there, and then you can still give it a name later. Okay, so URIs, to give them names, it's like naming people. Then you have the literals, all the atomic schema types, and then you have the blank nodes. And when you look at what goes where, basically, a subject can be a URI or a blank node, but you cannot have a subject that is a literal. So you cannot say 8 million is the population of Switzerland. You really have to say Switzerland has a population of 8 million, really has to go in the object. So the subject is either a URI or blank. The property must be a URI, right? So the verb of the sentence must always be a URI. And then the object can be anything, right? So you can say ETH is built on that ground that is a blank node, or ETH has a number of students of 23,000, then it's a literal, or ETH is in Switzerland, then that's a URI, right? The URI of Switzerland. For whom is that clear? Right? So this is the essence of RDF. Now, I directly gave you the model, the data model of RDF. It also has a syntax. Also not a surprise. We know we have that for every shape, right? We have syntax for trees, XML and JSON. We have syntax for tables like CSV. And so not surprisingly, we have syntax for these triples. Well, in fact, we don't have just one. We have many, many different syntaxes, but they all follow the same model. I'm giving you first the most popular one that is called Turtle. I think it's a pretty cool name. And it shouldn't surprise you that in a Turtle file, it's just a list of triples. So on every line, you have a triple: subject, verb, object, subject, property, object, subject, property, object. And imagine a very, very large list where you just list your triples. And then you parse that and you reconstruct the graph in memory, right? Now, a subtlety, because here you might be wondering why these prefixes and so on. We've seen them before in XML. These are called Q names, right? We have a prefix and a local name, and the prefix is attached to a namespace, right? That we've already seen before. However, there is something that would make all the XML people scream in the way that the triple store people use Q names. When they have a Q name, they do not see it as a pair with a namespace and a local name, where the namespace is represented by a prefix. Instead, what they do is they really concatenate together the namespace with the local name. So when they have this geo is located, it really means for them, this geo is located right here is really http://example.com/geography sharp is located. They really paste together that with that and get again a URI, right? So for them, the Q names are also URIs. So don't be confused by that. This is just how they do it. And so that is the reason why I said that this is in fact to the triple store people a URI. This is a URI that would be ethz.ch/sharp self. Then here, this is blah, 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 geography, sharp population. That's also a URI. And here it's a literal, right? Who is with me? All right. And so you have a point, just like at the end of every sentence, you just conclude your triple with a point. Then you have shortcuts, because when you build your graph, you might have nodes that have a lot of properties. You don't need to repeat them. You can repeat them, of course, but you don't have to. So for example, we can say that ETH is located in Switzerland and in Europe, and then I just put a comma there that says that it's located in these two places. So it means you have two triples, but in that triple, you repeat the subject and the property. Then if you put a semicolon instead of a comma, then you reuse just the subject. So here it means ETH, repeated here, has a population of 25,000. For whom is that clear? All right, very good. So now, very quickly, you don't need to worry too much about that. This is the JSON syntax. It's just a different taste, but it does the same thing. You have here, you typically factor all those that have the same subject into the same object in JSON LD. That's the name of the syntax. Here you have the subject, and here property, object, property, object, property, object. And then if you have triples with a different subject, you just do it with another object, right? So that's the JSON syntax. And then the XML syntax, it's always again the same thing. You have the subject right here, property, object, property, object, the URI, property, literal. When it's a literal, you just put it in there, okay? Do not focus too much about the details of the syntax. What I want you to see is just that there are three different syntaxes that basically represents the list of triples, turtle, JSON LD, RDF over XML. There's even more than that, but I don't want to scare you with even more syntaxes. All right? And here is just what I told you, that for the triple store people, when they see a Q name like that, what they actually do is they take geo, they take that, and glue it really with the local name that come from here. They really glue it together. This is the reason why very often they end their namespaces with a sharp sign, with the intent that the local name is basically glued to the sharp sign, and that makes it a fragment of some shared URL. Okay. So this is the RDF model. These are the syntaxes to represent RDF triples. And then you, of course, have a query language, just like we have SQL, JSONic, Cypher, GQL. Well, in the world of triple stores, the language is called SPARQL. Do not confuse SPARQL with Spark SQL. That's not the same thing. SPARQL is really specific to triple stores, right? And SPARQL looks like this. You don't need to learn it or anything. Again, that's just for your information, to give you an impression of what it looks like. You basically can select patterns. It's very similar to the pattern matching of Cypher, but in terms of triples, you basically see the triples you need. I want something, whatever, located in Switzerland, and I want to select it. So this here is going to locate, to find everything located in Switzerland, right? In Cypher, we would have done it with some ASCII art. And then you can have something more complex, like here you have S must be located in C, and C must be located in America, and then you select S. Again, in Cypher, you would have had ASCII art, right? But you see, who sees its equivalent to ASCII art, right? It's just a different way. And you can have then more clauses, you can have something more complex, you also have other clauses, order by, limit, and so on, right? So what do we learn here? Well, when people try to build a query language, they tend to use clauses, just like SQL. So this shouldn't surprise you that it actually also is yet another language that uses the same paradigm with all these clauses. Okay. Oh, by the way, because some people ask, because we see so many languages, at the exam, there's only 4. There's PostgreSQL, writing SQL queries against PostgreSQL. There is PySpark, right? Writing Spark jobs with Python, with the Spark API. There is SPARQL, that's the third one, so with data frames. Knowing that if you don't like SPARQL, you can also use data frame transformations instead. That's no problem. It's basically the same thing. So SPARQL, and then JSONic. Just these 4. For these 4, you will have it installed on the exam machines. You will have exam questions asking you to answer questions. All the rest, be it MongoDB, Cypher, and so on, that's only going to be theoretical questions, or we might show you some codes, not going, of course, into advanced details, and ask you questions, but you will not be asked to write anything in these languages, right? So you don't have to worry too much. PostgreSQL, SQL, PySpark, SPARQL, JSONic, and that's it, what you're expected to code. All right, so I hope that it removes a bit of your stress, because seeing so many languages, some of you might have wondered what's going to arrive at the exam. Okay. Now, yes?
Could we?
Maybe I need to switch it on.
Couldn't we just use a subset of Cypher to query, since triplets are in some sense a subset of labeled property graphs?
That's reverberated a little bit. Let me read it. Yes, so you can think of it in this way. You could also imagine that you would use Cypher in order to query triples, because Cypher is at least as powerful. Absolutely, you could imagine to do that. Then you just need to ask yourself, is Cypher not over-dimensioned for triples? It's a good question to ask. Maybe some people manage to actually take GQL, Cypher or GQL, and glue it in a way with triple source in a way that is more intuitive than using just a subset. But this is absolutely good thinking. You can absolutely imagine that you could use Cypher to query triples. I think it makes sense, right? Just to be clear, Cypher, so now consider it GQL, and SPARQL are 2 standards. SPARQL is a W3C standard, and GQL, I think, is an ISO standard. I think I had it on the screen a few slides back. I think it's ISO. Yes. Do I see? No, I don't know. It's ISO is the SQL one. Yeah. Okay. But anyway, 2 standards. All right. In practice, I mean, now it's a Lego game, the whole architecture. So technically, it's a common thing to do to try to adapt a language to a different environment and see if you manage to map it. So that's intellectually, it's a very interesting thing to do as well. Any other questions so far? Okay. So now, let's go to the part that can give a lot of headaches. But again, I shortened it to, and you don't need to worry or learn too much. It's just to tell you what people are actually doing with RDF. You know that if I tell you artificial intelligence today, you're probably going to think machine learning, ChatGPT, LLMs, right? But that is actually recent. If you go a few decades back, it wasn't so clear that artificial intelligence would actually be in the direction of machine learning, because back then we didn't have the computing resources. And so another approach to artificial intelligence was basically based on systems like the triple stores. It's to use this as a knowledge base, because if you consider every triple is basically a piece of information, just like the sentences you would have in ChatGPT, right? So an alternative to using machine learning for AI was to store the information in a knowledge graph and categorize the data as what is called an ontology, and then use it to reason on the triple store. And people are still working on that, because in fact, the reasoning is still an unsolved problem in artificial intelligence, right? ChatGPT is very good at talking, but it's not good yet at reasoning. And so this is still an approach. It might be not as popular as LLMs, but it is still something that attracts the attention of many people. So now, why do we need to actually why do we need to put some rules in the use of RDF? Well, RDF just allows you to do anything. It just allows you to say a subject or property object with any URIs, with any literals, with any blank notes. So basically, nobody would prevent me for putting in my triple store Schwyz, Ruchicha, Shlishoki, right? I could do that. But the thing is, it doesn't mean anything. And so the idea of an extra layer on top of RDF is to organize the meaning of the triples that we put in there. And so what people did is that they designed the concept of class, the concept of property, like class can be countries, people, universities, groups, fields, like if you go in mathematics, and so on and so on. So we have classes, we have properties, and then we use the triples in order to express formal statements about that. For example, we could say that ETH has the type school. We basically here categorize ETH in the class of schools, right? So then you can even go into category theory and so on when you do that sort of things in mathematics. But basically, once you have a knowledge base like this, like imagine an absolutely gigantic triple store. Imagine that people manage to do that at the scale of ChatGPT, that they actually manage to have billions or trillions or quadrillions of triples like that contain a formal representation of all the knowledge of humankind. And then you can use it in order to do entailments, like reasoning on the data, right? For example, this is a syllogism. All men are mortal. Socrates is a man. Therefore, Socrates is mortal. Then you can do reasoning. So this is the kind of the other AI that we have out there. Okay, that was actually my last slide now, just to tell you that this layer on top of RDF with the classes and properties and so on is called all, now all2. And it uses RDF. And I think a lot of people still use the XML syntax. That is still popular, but it's just a matter of taste, the syntax that you want to use. All right, so I'm done scaring you with all of this. Again, the idea here is just to give you this high-level overview, to know that it's out there, to show you that in addition to trees and tables, there are also graphs, and graphs follow the same idea of data independence with syntaxes, query languages, and so on. Standardization is very important. Yeah, that's pretty much it. Now, the only thing that is left in the lecture is basically cubes, yet another data shape. I'm going to present it to you next week on Tuesday. On Wednesday, there will be a guest lecture by Oracle Labs. I sent an announcement. Did you get it in Moodle? Yeah. So we will have people from Oracle Labs telling you about vector databases. That is just yet another shape, so graph, cubes, and vectors. And I told them to try to focus a little bit on put it in the context of all these data shapes and data independence. So I'm looking forward to their talk. It's the first time that they give it. It's relatively new, and I hope you will enjoy it. Now, I would like to use, I timed for it the remaining 10 minutes. You should have received a course evaluation email. Did you? So ETH encourages to give you the time during the lecture to actually fill it. So now you can just open that email if you haven't already done so and fill the course evaluation. And then at 10, you will be good to go. So it's very important to us, the course evaluation, because we really try to improve the course every year. You see that you probably noticed the slides are not even the same as before because I keep changing them. And so I really try to have an open ear for all the suggestions of how we can keep improving the course, basically for the people in a year from now. So examples of what came out of that is the textbook, right? I did the textbook because some students a few years ago asked for it consistently in the course evaluation, and this is how the textbook Westbourne. By the way, if you're done, you're free to leave. I'm going to abstain from giving information about the exam today and do it next week. All right, so I see a lot of you are going. So thank you, everybody. Goodbye, and see you next week on Tuesday. Thank you very much.